Okay, in this module, we are going to look at the link prediction techniques. So, link prediction is a very useful thing in a social network because, given a network, you want to kind of find out what new links will appear in the network over time. Okay, so in dynamic networks like social networks, this is very important to know because you can do some prediction of the changes in the network topology over time and do some analysis based on that. Now, in this module, we'll focus only on new links appearing, and we're not going to focus on the existing links disappearing. Okay. All right. So and we'll also focus specifically on what is called the neighborhood-based link prediction techniques, which are observed to be computationally efficient and also they are kind of effective compared to other techniques out there. Now we are going to look at three based link prediction techniques: the preferential attachment technique, the atomic Hadar coefficient, and the Jaccard index. Okay, so the neighborhood link based prediction techniques, of course, as the name itself indicates, you're going to look at the neighbors of the vertices. So we'll use this notation like n of I to indicate the set of neighbors of node I. So the cardinality of this set is the number of neighbors of node I. So all the link prediction techniques are designed to compute a score called the link prediction score for any two nodes in the network that are not yet connected. And when you want to pick a new link or when you want to do a prediction of which new link will be created, the node pair with the largest positive link prediction score is chosen to be connected with a link, or is chosen to be the node pair that will have a link between them. And if there's a tie, we typically break them arbitrarily. Okay, so now let us start looking at the three techniques. So the first is the preferential attachment technique. So as I said before, so for each node pair that are not yet connected, we will compute a score. Okay, so in this case, we'll call it as a PAC score for the preferential attachment. So for a node pair ij, the preferential attachment score is the product of the degrees of the nodes I and j. So the number of neighbors of a node is also called the degree of the node. So in order for a node pair ij to be chosen under this technique, you want the PAC score to be high, and the PAC score for a pair will be high if at least one of the two nodes have a larger degree. So if both the nodes have a larger degree, then their product will also be larger. And now you can see if two nodes have a smaller degree and they are not yet connected, the product is going to be relatively smaller. So which node pairs have a higher chance of getting selected for a chosen for a link to be created is going to be the nodes that have a larger degree. Okay, so under this preferential attachment measure, you are more likely to have the network evolve as a scale-free network, where a scale-free network is a network where majority of the nodes have a smaller degree, but there are few nodes that have a very high degree, and the low degree nodes are connected to the high degree nodes. So the high degree nodes is called a hub. Okay, so like an airport network is a scale-free network where majority of the airport nodes have small degree, but there are appreciable number of nodes at the high degree, like called the hub airports, to which the low degree nodes or airports are connected to. So the airports network is typically an example of a scale-free network, and you can always think about it if you want to understand a scale-free network. Alright, so let us do this example. So you have here say 8 nodes, and this is existing network, and you want to do a prediction if at all I need to if at all a link will be added to this network, which node pair will be connected with that link. Okay, so again we are doing a prediction, we are not kind of saying 100% sure that this is the link that will be created or that will form if you want to add a new link. Okay, so again the link that will form could be different than what you say what you do as a prediction. So later we'll analyze the kind of efficiency of each of these techniques. Okay, so as a first step, write down the degrees of the vertices. So these are the degrees of these nodes. Now then list the node pairs that are not yet connected. So for 1 it's connected to 3, 4 and 7. So it's not connected to 2, 5, 6 and 8. So 1, 2, 1, 5, 1, 6, 1, 8. Then 2 is connected to 3. So not connected to 3. So 2 is connected to 4, 5 and 7. So 2 is not connected to 1, 3, 6 and 8. Now you should realize that if you're doing the analysis for 1, 2, it is as well as good doing it also as good as doing for 2, 1, 2. So you're not going to list 2, 1 here. So 2, 3, 2, 6, 2, 8. So by now you should realize that. So in a node pair, I is always less than j. Okay. So then for node 3, it is connected to 1 and 4. 3 2 would have been already taken care of. So you have to now look at only 3 5, 3 6, 3 7 and 3 8. Now in the case of 4, it's connected to 1, 2, 3, 5, 6. So it should be connected, or it should connect only 4, 7 and 4, 8. In the case of 5, it's already connected to 2, 4. So these are low ID nodes. So 2, 1 through 3, 4 already considered or connected already. Then 6 is already connected. So 7, 8 is already connected too. So 5, 7 is only node pair. In the case of 6, this got all the lower IDs. So it's connected to 8. It's not only connected to 7. So you say 6, 7. So these are the node pairs that are not yet connected. Now you have the degrees of the nodes. So all you have to do is take a product of the degrees of the nodes. So for the pair 1, 2, the PAC score is going to be the degree of 1 times the degree of 2. So it's 3 times 3, which is 9. For the pair 1, 5, its PAC score is degree of 1 is 3, degree of 5 is 4. So 3 times 4 is 12. For the pair 1, 6, its PAC score is 3 times 3, which is 9. For the pair 1, 8, it's going to be 3 times 2, which is 6. So you compute the PAC scores of all the node pairs and pick the node pair that has the largest PAC score, which is in this case 1, 5, and there's no tie. Okay, so that is the predicted link. Now the atomic Adar coefficient, we can indicate it as AAC, gives preference to node pairs that have more common neighbors but with a lower degree. So you look at the formulation here. So for any node pair ij, you find all the common neighbors of the two nodes I and j, and then use this formulation. So k is all the set of common, so k will represent the common neighbors. So logarithm of the degree of those common neighbors, and then 1 over that logarithm value. So that is why I said it gives preference to node pairs that have more common neighbors, because you will be considering more k's, more neighbors, but those neighbors with a lower degree. So if you have a lower degree value for k, n of k and log n of k is going to be smaller, and 1 over that a smaller value is going to be larger, and you're summing it up. So that's why you need more common neighbors but with a lower degree. Okay, so because each of these fractions, or 1 over this, is going to be a fraction. So it's going to be a logarithm of n of k. If it's a small number, n of k is a small number, log of that value is going to be a small number also. So it could be a fraction, it need not be a fraction, but basically it's a smaller number if n of k is smaller. So 1 over a smaller value is going to make it larger, and you're going to sum those values. So if there are no common neighbors for a node pair, then the AAC score is 0. So that means in order to get a positive greater than 0 score for a node pair, they have to have at least one common neighbor. So you could say that is kind of a difference between the PAC measure and this measure, because the PAC measure could predict a link between any two nodes. They need not even have a common neighbor. Whereas the AAC measure is formulated in such a way that it will do a prediction for a link between two nodes only if they have at least one common neighbor already. Okay, and it is giving preference to neighbors that have a lower degree also. Okay, so let us do this for the same graph. So what we need to find out is, since we need to know the common neighbors, we need to write down the list of neighbors for each node. So for each node, say 1, you have 3, 4 and 7 as the neighbors. For 2, 4, 5, 7 as the neighbors, and so on. So we can write down the convention in increasing order of the neighbor IDs. Alright, so the number of neighbors is the degree. So you can find the logarithm of the degree. So the degree is 3, so log 3, again log is to the base 10. Then log 3 again 0.4771, log 2 is going to be 0.3010, log 5 to the base 10 is 0.6989, and then 1 over that log degree. So just compute the inverse of these logarithm values. So that is 1 over log degree. Now you write down all node pairs that are not yet connected, which we already saw how to write it down. So again, basically for a node pair, I is going to be less than j. So for 1, you're going to consider everything above 1. So and then rule out the things with which 1 is already connected. So 1 is connected to 3, 4 and 7. So the node pairs you need to consider 1, 2, 1, 5, 1, 6 and 1, 8. 2 is already connected to 4, 5 and 7. So you need to consider 2, 3, 2, 6 and 2, 8. Not 2, 1, because you already considered 2, 1 when you considered 1, 2. Now 3 4 is connected to 4, but not with 5, 6, 7 and 8. Then 4 is connected to 5, 6, but not to 7 and 8. Then 5, again, when you look at a vertex, just consider the vertices above with a higher ID. So for 5, don't need to consider anything below 5. And then 5 is connected to 6, but not to 7, but to 8. So just consider 5, 7. The case of 6 is not connected to 7, but to 8. So just consider 6, 7. So now, once you have the common neighbors, now we are going to find the common neighbors. So I just explain how to write the node pairs. So now to find the common neighbors, all you have to do is take the intersection of the set of neighbors. So for the pair 1, 2, you have 3, 4, 7 for 1, 4, 5, 7 for 1. So just you have to find the intersection. So for it's 3 is not here, but 4 is here and 7 is here. So it's good enough. So just use one set and see if every value there is in the other set. So 4, 7 is the set of common neighbors. For 1, 5, 3 is not here for 5, 4 is not here in the neighbors of 5, 7 is not here in the neighbor set of 5. So that means it's an empty set. So if a node pair has no common neighbors, their AAC score can be right away written as 0. Now for the node pairs that have common neighbors, all you have to do is, like in this case, you have common neighbors 4 and 7, you have the 1 over log degree value for each of the nodes. So for 4, it's 1.4308. For 7, it is 3.3222. So you have to just add those values. 1.4308 plus 3.3222 is going to be 4.7530. Now the pair 1, 6, again look at here. So 3 is not here among the neighbors of 6, 4 is here, then 7 is not among the neighbors. So the common neighbor is just 4, and its 1 over log degree score is 1.4308. So one more case, so the pair 2, 3, you have 2, 4 is here, but no 5 and no 7. So 4 is the only common neighbor, so the score is 1.4308. So once you get the AAC scores of all the node pairs, just pick the node pair that has the largest AAC value. So in this case it will be 1, 2, and that is the link that you have predicted. Now for the same graph, the PAC measure predicted 1, 5, but in this case AAC measure predicted 1, 2. Okay, so the third prediction technique is called the Jaccard coefficient based technique, and it is computed as the Jaccard coefficient score for a node pair ij is computed as the ratio of the intersection of the neighbor sets and the union of the neighbor sets. So intersection, you all know, you just need to find the common neighbors, right? Now for union, you need to consider each vertex exactly once when you find a union, because if you have common neighbors, you could think that you need to write down the common neighbors twice in the union. No, you have to include a vertex only once in the union. So because of this, the JAC score will always range from 0 to 1. Now the other two scores, PAC and AAC scores, if you remember this, so they could be less than 1, greater than 1, anything. So you cannot say the AAC or PAC scores will be in a certain range, whereas you can say the JAC score will be in a certain range, 0 to 1. So based on that, you can then also say that closer the score to 1, the larger chances for the notepad to have a link. Closer it is to 0, lower the chances for the notepad to have a link between them. Okay. Now, again, if notepad does not have a common neighbor, the intersection will be an empty set. So the size of the intersection will be 0. So the JAC score will be 0 divided by the union. So of course it is going to be 0. So you see here, in this sense, the AAC and the Jaccard coefficient technique have some similarity, because even there you need to have at least one common neighbor in order to have a positive AAC score. Same thing here for JAC score, you need to have at least one common neighbor. If two nodes do not have a common neighbor, their AAC or JAC score will be 0. So almost likely that the notepads are not going to be considered unless there's a tie where all notepads, the JAC score is 0. Okay. So that this way, the first technique, which is the preferential attachment technique, is different from the other two techniques, because that's the only technique among the three techniques that could link any two nodes. They need not have a common neighbor. Okay. So let's take an example. So again, we need to write down the neighbors for each node, and then write down all the notepads that are not connected and find the intersection of the neighbor sets. Already explained in the previous case how to use the neighbor sets and find the intersection. So just pick one set and see if any vertex in that set is in the other sets too. So using then you have also take the union of the neighbor sets, which is not needed here. Alright, so how to take the union? So the pair 1, 2, you have 3, 4, 7, 4, 5, 7. So write down 3, 4, 7, or just have the neighbor set of 1 as the initial union, and then go to the other set and see if any value is there in the already evolving union. If it's there, don't include it. If it's not there, include it. So 4 is already here in this set, so don't include it. Then 5 is not here, included. 7 is already here, so do not include it. So 3, 4, 5, 7 is the union of the two set of neighbors. Then of the neighbors of the two nodes 1 and 2. Now all you need to do is, in the formula, just take a ratio, so intersection divided by union. So again the sign, so 2 divided by 4, okay, so that's 0.5. Now do such an analysis for all the notepads. Say for example 1, 5, this is a neighbor set for 5, and 5 for 1, and then for 5 you have 2, 6, 8. It's clear that they don't have anything in common. 3 is not here, 4 is not here, 7 is not here. So the intersection of the neighbor sets is 0. The union of the neighbor sets, which is not necessary to be found out, because whatever it is, the ratio is going to be 0. But just for curiosity, let's go and find it. So for 1 and 5, you have 3, 4, 7. So see if 2 is already in this set. No. So include 2. Then 6. No. Then 8. No. So it's going to be 2, 3, 4, 6, 7, 8. So 0 divided by the size is 6 for the union, so it's still 0. Now 1 and 6, the intersection is 3 is not here, 4 is here, 7 is not here, so just 4. And then the union is 3, 4, 7, 4 is already in the union, then 5 is not here, 8 is in the union. So 3, 4, 5, 7, 8. So then the ratio is going to be 1 over 5 to 0.2. So once you find the Jaccard scores like this for all the node pairs, pick the pair that has a larger value for Jaccard score. If two or more pairs have a tie, just write down all the pairs and say that these are the predicted links. So one in this case, the Jaccard score is 0.5. That's the largest. So the corresponding node pairs are 1, 2, and 2, 6, and those are the links that you are predicting. Okay, so we'll stop the video with this.